Okay, great. So I'm going to start. Our title for our research paper is Macroscopic Experiments of Remagnetization, Finite-Time Flipping Regime and the High Field and Frequency. So, motivation for our work. Firstly, we look at the classical macroscopical torque theory predictions, which predict the three regimes. Which one is synchronous, precession, and liberation, and obviously also bistable regime, where depending on initial conditions, torque model prediction says that ball or particle in our case will go either in a precision or liberation regime. And looking at the current theory, we we see that reaching high frequency and high field, where classical macroscopical torque theory fails, we observe a duality of regimes where its lag angles movement follows the liberation regime model, and which three-dimensional model follows the precision regime, which this theory does not predict. Therefore, we saw that there's necessity to extend the current theory for these high-frequency, high-field regimes, and define this new region for macroscopical torque model. So main objectives. First one is we create a 3D model particle using PLA, and we do experiments testing different regimes and qualifying existing liberation, precision, and synchronization areas, as well as we go for certain frequencies and observe the change from one regime to the other to directly calculate the underlying borders of different regimes. Therefore, afterwards, we identify and characterize this new regime and look at its dynamics and different egg yolk type for equations that describe it, and look what the influences, for instance, from inertia are coming on from. And afterwards, we extend the current theory in order to explain our observed phenomena. So let's look a bit about a theory. So on equation 1 and 2, you can see the egg yolk type equations describing the relative motion of the magnetic moment and the whole particle in a glycerin. And on figure 1, you can see the classical macroscopical model of particle rotation is describing three regimes. And these both are fundamental for our research, as the figure 1 it shows the classical theory and lets us observe and confirm our experiments correctness and truthness, as well as afterwards equation 1 and 2. Let's expand the current theory for macroscopical model. So looking at the methods, first of all, we created a cross-shaped a ball model containing a cavity for a magnetical ball, and the other half the same cavity for another ball, creating this called remagnetization model, where internal balls in a cavity filled with glycerin act as a egg yolk and create this remagnetization, as they tend to stand directly one after another. And in the figure 3, you can observe or developed cavity to place magnetical particle directly inside the center of the Helmholtz coil system and ensure that it does not change its position, as well as this container is filled with the glycerin. And in order for the glycerin not to change its density during the experiment and therefore affect the results of the experiment, uh, on the up of the container is placed transparent polymer glass lid, ensuring that water from air does not contaminate the glycerin. As you can see, we used a three-dimensional Helmholtz coil system consisting of three coil systems in each direction. As well, on upper side we placed the Bessler black and white camera for high definition images, and as already seen, the container is placed in the middle of the Helmholtz coils, filled with the glycerin, and this is called Remagnetization part. So for data processing, we used Python algorithm, which captures the ball's images and taking from its geometry, where the ball is manufactured in one side white and the other side black, which ensures that we can observe its three-dimensional magnetical moments offset from X and Y plane, thanks to the black side creating an ellipse. And by determining the minor and major axis for the ellipse, we can determine its three-dimensional moment, as well as looking at the center of the ball and the black region, center of mass. We can obtain the magnetical moment in a XY plane. Coming from that, we can determine the lag angle as we recorded as how much coils were connected to the programmable current generators, and we could obtain the exact specific timeline current measurements from the coils, and therefore using a data frame time of capturing, we could align coil data with the determined three-dimensional data from the images, and using that we could determine the lag angle and the theta angle to later on display these data on a graph. As you now can see, figure 6 contains lag angle alpha and the theta angle from XY plane for 16 millitesla and 8 hertz, which in our experiment and the macroscopic torque graph would be at a high frequency, high field region, where, as we now know, the classical model fails, and we observe a duality in regimes where ball tends to ball of magnetical moment tends to go near 90 degrees state and stay there, as well as lag angle creates that so-called back and forth movement. And this duality is not currently explained by any theory. Therefore, first of all, we observe this duality of regimes where magnetical moment does not anymore stay in XY plane and goes to the precision regime, as well as the back and forth movement. We observe that this particle stays close to 90 degrees, which aligns with extended theories with the inertia predictions. And moreover, we create a real-time experimental simulation for axial particles, and show that that aligns with the classical theory, as well as let us examine regimes that are not really available at the nanoscale. Nanoscale. Yeah. Thank you for your attention. Any questions?
Thank you for the nice presentation. Let's move on to Q&A session. Does anyone have questions? So, could you explain again how to define the orientation of magnetization?
Okay, so mainly we have these two magnetical balls inside the cavities in this printed PLA ball, and then as the PLA ball is printed into two halves, one black and one white, each containing a one ball inside of it. We then have the image from the upper Bustler camera, and as we see the black and the white part, with for instance, if it goes out of the XY plane, then obviously the black side or the white side goes upper the black other side, and it creates this called ellipse. And then we just determine the ball's center using Hughes circle detection and calculate the distance from the center to the ellipse's outer lining, and then from that we can calculate the theta angle and alpha and alpha angle just comes from if we can determine the center of the ball, and we can determine the black region's center of mass, it is like center, then we can draw a line connecting them both, and it would be the magnetical moment of the ball.
Oh, thank you. So, does anyone have questions? So, it's almost time. So let's thank the speaker again. Thank you for the interesting presentation.